Hello and welcome to the fourth lesson of our third unit factoring in our grade 10 academic math class. Today we're looking at, I guess, our sort of third way of factoring. We've got common factoring, factoring trinomials, both tricky and simple trinomials, and now on to factoring differences of squares. So I've got this first part kind of filled in, so if you need to, you can pause the video and just sort of fill this beginning piece in. It's really just an explanation of how do you identify what a difference of squares is, and subsequently how can we use knowing what a difference of squares is to work our way backwards to the two binomial factors that lead to it. So without further ado, let's get to it. A difference of squares, let's just focus in on our first example here. As a proof of concept, we actually work forward from this set of binomials that we have just up here at the top. And the set of binomials is x plus 5 and x minus 5, each in brackets. So what you'll recognize right out of the gate is that these two binomials are the same, except that they have opposite signs in the brackets. How does this play out if we were to expand it out? You'll see that we have an x squared at the beginning and we have a negative 25 at the end, and the two middle terms, the minus 5x and the plus 5x, are the same term with different signs. So as you move through the simplifying process, these two terms undo each other. They're gone. So you're left with this unique two-term binomial. What do we notice about this two-term, or I guess it's a binomial quadratic, is what I mean to say. So there's two terms, but it's a quadratic. And what we notice is that the first term is a perfect square, meaning that there's two identical things multiplied together to give you the result, which is x squared. And the 25, our last number, is also a perfect square, in that there are two identical numbers, 5, that multiply together to give you that 25. So that's part of our patterning that we're looking to notice here, is that the first and last terms are perfect squares and they're separated by subtraction. That's why we call it a difference of squares. Let's look at our second example. Same idea here. If we're starting from two identical binomials with different signs, x minus 2y and x plus 2y. So the first term is just a perfect square again. X times x gives you x squared. The last term, 4y squared, is a perfect square, 2y times 2y. And again, you have these two opposite signs inside the brackets, which when you expand it out gives you plus 2xy minus 2xy. They undo each other. So this middle term essentially doesn't exist anymore. It undoes each other. And we're left with a perfect square and a perfect square separated by a difference. So really, in terms of the procedure for us, we are going to be going in the other direction. We're going to be striving to say, all right, imagine I gave you this to start with. How do I know what to do to move back to that, a factored form of this? That's what we're going to look at today in terms of the procedure. So let's jump right in. Here's our first example. We have x squared minus 36. So the first thing we want to do, and again, I'm trying to model what I'm thinking here, is this in fact a difference of squares? Are there two terms? Yep. Are they separated by a difference? Yes. Are each of the two terms perfect squares? Yes. So procedurally, we are going to take our two-term quadratic and we are going to factor it down into two identical binomials. So how do we figure out what's going to go in these brackets? We know that one's going to get a minus and one's going to get a plus. And if you're wondering, it doesn't matter whether the plus or the minus goes in the first bracket. They can be flipped. It doesn't matter. The order's not important. Since it's being multiplied, you can multiply the first thing by the second or the second thing by the first. You're going to get the same answer. So the way that I'm going to model how to do this is, in recognizing that this is a perfect square, I'm going to find the square root of that first term. So the square root of x squared is x, and the square root of my last term is 36. Of 36 is 6. I want to point out that that negative that we have hanging out in the middle here, it is not included over here. It really just tells us that we're dealing with a difference of squares rather than something different. So we've taken the square root of the first term. Those become the first terms in our brackets. And we take the square root of the final term, and that becomes the last term in each of our brackets. And that's how you go about factoring a difference of squares. First identifying it, and then taking the square root of the first and second items, and then putting a negative and a positive in the brackets. Let's have a look at another example. Here we have 9x squared minus 25y squared. So same thing. Is this a difference of squares? Well, the first term, so there's two terms. That's a start. Separated by subtraction, so it's a difference. Also good. Is the first term a perfect square? It is. Is the second term a perfect square? Yes, it is. So we have a difference of squares here. I'm going to look for the square root of the first term, so 9x squared. And if you have a term that has sort of multiple parts, like a coefficient and a variable, I just tackle them sort of one at a time. So what is the square root of 9? 3. What's the square root of x squared? X. So there's the square root of our whole first term. And now we're going to take the square root of our second term, 25y squared. Square root of 25 is 5. Square root of y squared is y. I have the two terms that are going to make up the contents of my brackets. So let's get those brackets happening. Starts with the square root of the first term, 3x. Ends with the square root of the last term, 5y. One gets a plus, one gets a minus. And just to say it again, you can have this totally the other way. You could put the subtraction first and then the addition. Order of those signs in the brackets doesn't matter. So there we have it. Let's have a look at another example. 100 minus x squared. So is this a difference of squares? It's got two terms, separated by a difference. Is the first term a perfect square? It is. Is the second term a perfect square? Yes, it is. So let's work through it. We're going to find the square root of the first term. It's going to give us 10. Square root of the second term gives us an x. All right, let's pause here. You try to fill in the two brackets here. When you have an answer, come on back and we'll see how you did. Okay, let's get a look. Two brackets. They start, each of them, with the square root of the first term, which is 10s. They finish with the square root of the last term. Those are x's. One gets a plus, one gets a minus. Or you can write those in the other order. Okay, let's have a look at another example. Okay, so here we're just adding layers of complexity. The idea is still the same. Is this a difference of squares? Well, it has two terms. It's separated by a difference, which is like this visible minus right here. Is the first term a perfect square? So if you're not sure, just have a look at each of the components. Are there two identical things that multiply together to give you 16? Are there two identical things multiplied together to give you x squared? And are there two identical things multiplied together to give you y squared? If that is true, then that is a perfect square. Same thing, is 49 a perfect square? Is z squared a perfect square? If this is true, we can just start rocking on it. So let's take the square root of 16x squared y squared. Square root of 16 is 4, square root of x squared is x, and the square root of y squared is y. And let's find the square root of our final term. Square root of 49 is 7, square root of z squared is z. And now we build some brackets. So same thing here. I'd like you to try to finish this question on your own. So hit pause, finish it up, and then when you got it done, come on back and we'll see if you got it right. Okay, let's get a look. We've got two brackets. Each of them are going to start with the square root of my first term, and each of them is going to end with the square root of my second term. One gets a plus, one gets a minus. And there it is. Let's keep going. Example E. So is this a difference of squares? Let's have a look. We have two terms. Yep. First term is a perfect square. Second term is a perfect square. However, it's not a difference of squares. This is addition. So this is already fully factored. Can't do any more here. If it's not a specific difference of squares, then you can't go any further. If it's a plus in there, it doesn't work. And the reason is, if we go all the way back up here to the beginning, this negative that you end up with, let me change up my colors here. This negative that you end up here, it comes from the fact that you have a plus and a minus in these brackets that have undone this second term, that make it so it doesn't exist. If you had a plus down there, that wouldn't be the case. So that one is already fully factored. No more that we can do there. Let's keep moving along. Again, this is just looking more complicated, but it's not particularly more complicated. If we have two terms, which we do, and they're a difference, which it is, we just have to see if we can square root the first term and square root the second term. What's nice about this is even though they're fractions, the square root of that first term, 49 over 64 x to the exponent 4, the square root of 49 is 7, the square root of 64 is 8, and the square root of x to the exponent 4 is x to the exponent 2. So this totally works. Let's have a look at our second term. 81 over 25 y squared. The square root of 81 is 9, the square root of 25 is 5, and the square root of y squared is y. So the terms are more complicated, but they're not, it doesn't make them any less perfect squares. So let's try to fill these monsters in. And draw some tall brackets this time because we got some fractions going on. So we're looking for the square root of the first term to start each bracket, and the square root of the second term to end each bracket. One gets a plus, one gets a minus. And there you have it. Complicated? Yep, but it's the same principle that we've been employing the whole way along. All right, let's have a look at this one. Actually, the video is getting a little bit long. Let me pause here. I know we only have 2 left, but let's pause here. And before we tackle these last 2, let's head to a part 2 on this video.